Hello friends. I am Satish Lele. This video is part of my chemical process piping channel on YouTube. This video is about gas and steam turbine. A large percentage of world's power generation is achieved using steam turbines. The advantage of power generation using steam turbines are the physical properties of steam used as energy source for the turbines are predictable at various pressures and temperatures and are constant across the globe. The steam turbine designs are scalable and can be designed to suit any application.
The steam turbine separates the energy source and electrical power generation, making it compatible with various sources of fuels as feedstock, coal, biomass, municipal waste, gas unlike the gas turbine, gas engine, diesel sets, etc. Combined heat and power can be handled by steam turbines effectively, making it a widely used mode of power generation in process industry. By virtue of its operational characteristics, starting time and reliability, these turbines suits better, catering to the base load operation in modern power systems.
The steam turbine changes chemically stored energy into mechanical energy, too. It's called the heat force engine. The steam turbine works similarly to the water turbine, which is known probably by everyone. Not water, but steam is used as working medium. Turbine types. When people began to use water power to win mechanical work, they looked first for the best forms of impellers. 3 types were established thereby, and variations of them are used today in various applications, among others steam turbines in power stations, as marine propellers, as compressors in gas turbines, etc. The Pelton turbine. The Pelton turbine, also free jet turbine, was invented 1880 by L.A. Pelton. It possesses spoon-shaped shovels. The jet hits the impeller tangentially, gets divided by the 2 shovels and transfers an impulse. The Pelton turbine is used in storage power stations with downward radiance up to 2,000 meters and can contain up to 6 nozzles. The Kaplan turbine. The Kaplan turbine, developed around 1915 by the Austrian V. Kaplan, looks like a marine propeller. The jet is laid there by axially on the freely adjustable shovel pages. Mode of operation of the steam turbine. Since it is a steam jet and no more a water jet meets the turbine now, the laws of thermodynamics are to be observed now. The modern steam turbine is an action turbine, no reaction turbine, i.e. the steam jet meets from a certain nozzle a freely turning impeller. There's a high pressure in front of the turbine, while behind it the low pressure is maintained, so there's a pressure gradient. Steam shoots through the turbine to the rear end. It delivers kinetic energy to the impeller and cools down, thereby the pressure sinks. Steam is produced in a steam boiler, which is heated in power stations by the burn of coal or gas or by atomic energy. Steam doesn't escape then, but after the passage through the turbine it is condensed in a condenser and then pushed back into the steam boiler again by a pump. This has the advantage that, for example, in nuclear power stations, work and cooling water are clearly separated. Multi-level steam turbines. In modern steam turbines, not only one impeller is propelled, but several being in a series. Between them, idlers are situated, which don't turn. The gas changes its direction passing an idler, in order to perform optimally work again in the next impeller. Turbines with several impellers are called multi-level. The principle was developed 1883 by Parsons. As you know, with the cooling gas expands. Therefore it is to be paid attention when building steam turbines to a further problem. With the number of passed impellers also the volume increases, which leads to a larger diameter of the impellers. Because of that, multi-level turbines are always conical. Cousin of several turbines. In power stations today, different types of turbines are used in a series, e.g. 1 high pressure, 2 medium, and 4 low pressure turbines. This coupling leads to an excellent efficiency over 40%, which is even better than the efficiency of large diesel engines. This characteristic and the relatively favorable production make the steam turbine competition less in power stations. Coupled with a generator and fired by an atomic reactor, they produce enormously much electric current. The strongest steam turbines achieve today performances of more than 1,000 megawatts. Gas turbine. Gas turbines are a type of internal combustion IC engine in which burning of an air-fuel mixture produces hot gases that spin a turbine to produce power. It is the production of hot gas during fuel combustion, not the fuel itself, that gives gas turbines the name. Gas turbines can utilize a variety of fuels, including natural gas, fuel oil, and synthetic fuels. Combustion occurs continuously in gas turbines, as opposed to reciprocating IC engines, in which combustion occurs intermittently. How do gas turbines work? Gas turbines are comprised of 3 primary sections mounted on the same shaft: the compressor, the combustion chamber or combustor, and the turbine. The compressor can be either axial flow or centrifugal flow. Axial flow compressors are more common in power generation because they have higher flow rates and efficiencies. Axial flow compressors are comprised of multiple stages of rotating and stationary blades or stators through which air is drawn in parallel to the axis of rotation and incrementally compressed as it passes through each stage. The acceleration of the air through the rotating blades and diffusion by the stators increases the pressure and reduces the volume of the air. Although no heat is added, the compression of the air also causes the temperature to increase. The compressed air is mixed with fuel injected through nozzles. The fuel and compressed air can be pre-mixed, or the compressed air can be introduced directly into the combustor. The fuel-air mixture ignites under constant pressure conditions, and the hot combustion products gases are directed through the turbine, where it expands rapidly and imparts rotation to the shaft. The turbine is also comprised of stages, each with a row of stationary blades or nozzles to direct the expanding gases, followed by a row of moving blades. The rotation of the shaft drives the compressor to draw in and compress more air to sustain continuous combustion. The remaining shaft power is used to drive a generator which produces electricity. Approximately 55 to 65% of the power produced by the turbine is used to drive the compressor. To optimize the transfer of kinetic energy from the combustion gases to shaft rotation, gas turbines can have multiple compressor and turbine stages. Because the compressor must reach a certain speed before the combustion process is continuous, the self-sustaining initial momentum is imparted to the turbine rotor from an external motor, static frequency converter, or the generator itself. The compressor must be smoothly accelerated and reach firing speed before fuel can be introduced and ignition can occur. Turbine speeds vary widely by manufacturer and design, ranging from 2,000 revolutions per minute RPM to 10,000 RPM. Initial ignition occurs from one or more spark plugs depending on combustor design. Once the turbine reaches self-sustaining speed, above 50% of full speed, the power output is enough to drive the compressor. Combustion is continuous, and the starter system can be disengaged. Gas turbine performance. The thermodynamic process used in gas turbines is the Brayton cycle. Two significant performance parameters are the pressure ratio and the firing temperature. The fuel-to-power efficiency of the engine is optimized by increasing the differential ratio between the compressor discharge pressure and inlet pressure. This compression ratio is dependent on the design. Gas turbines for power generation can be either industrial heavy frame or aero-derivatives designs. Industrial gas turbines are designed for stationary applications and have lower pressure ratios, typically up to 18:1. Aero-derivatives gas turbines are lighter weight, compact engines adapted from aircraft jet engine design which operate at higher compression ratios, up to 30:1. They offer higher fuel efficiency and lower emissions, but are smaller and have higher initial capital costs. Aero-derivatives gas turbines are more sensitive to the compressor inlet temperature. The temperature at which the turbine operates, firing temperature, also impacts efficiency, with higher temperatures leading to higher efficiency. However, turbine inlet temperature is limited by the thermal conditions that can be tolerated by the turbine blade metal alloy. Gas temperatures at the turbine inlet can be 1200 degrees centigrade to 1400 degrees centigrade, but some manufacturers have boosted inlet temperatures as high as 1600 degrees centigrade by engineering blade coatings and cooling systems to protect metallurgical components from thermal damage. Because of the power required to drive the compressor, the energy conversion efficiency for a simple cycle gas turbine power plant is typically about 30%, with even the most efficient designs limited to 40%. A large amount of heat remains in the exhaust gas, which is around 600 degrees centigrade as it leaves the turbine. By recovering that waste heat to produce more useful work in a combined cycle configuration, gas turbine power plant efficiency can reach 55 to 60%. However, there are operational limitations associated with operating gas turbines in combined cycle mode, including longer startup time, purge requirements to prevent fires or explosions, and ramp rate to full load. Thanks for learning. If you like this video, please give a like to my channel and subscribe it.